Hi, my name is Thomas Zulper, and this is the project overview for heat pump design in Thermo-Fluid Systems Design course at the University of Wisconsin-Platteville. A heat pump is essentially a reverse air conditioning system that uses the heat in the ground, that is to say, geothermal heat, and makes use of a refrigerant that can pump that heat out of the ground and provide it to buildings to use instead of natural gas or propane, the most common heating sources. Now, the benefit of a heat pump is that it's essentially an air conditioner acting in reverse. So the figure on the left shows the heat pump activity. On the top, we've got a building shape, in this case, just a roof and rectangular enclosure. We've got a heat exchanger and covering the condenser. Then the square in the middle is the actual refrigeration loop, performing essentially the same function as a refrigerator in reverse. And on the very bottom here, we've got what's referred to as the ground source, and a second heat exchanger pulling heat from the ground, transferring it to the refrigerant, and then releasing it into the building. Now, as I said, these work as air conditioners as well, which actually pull heat from the building, draw it into the refrigerant, in this case, more or less an air conditioning or refrigeration cycle, and then dump that heat into the ground. So, the project that the students will be undertaking is to design a heat pump system for the Platteville Mining Museum. They want to lower their heating bills, which are currently based on natural gas, and they're subject to the restriction that the exterior of the building cannot be altered. And then the ground in the Platteville area is stone, and as the name Museum indicates, there are actually mines underneath that museum. So here's a photograph of the museum itself, the brick exterior with the stone near the foundation, which is prevented from any alterations, at least on the exterior of the building. So I'll ask the students to design a heat pump to replace the natural gas furnace, specify the loop field, select the refrigerant, determine the operating points, that is to say pressures and temperatures, size the heat exchangers, how many tons of heat must they exchange, and the piping network as well, and then select compressor, pumps, and fans, and estimate the upfront costs and operating costs. Now, to provide a lead into this, you could say I'm designing a heat pump for my house as well, and you could follow my approach. So, first, we have to model the building, and you'll see the approach that's pretty convenient is just to use a rectangular prism and calculate the areas of all the walls and roofs that are exposed to the environment. And then cross-check with the energy bills. This is actually a way that you can determine the specific composite R value of the building. Then we want to determine the maximum heating load, like what heat must be provided on the coldest day of winter. Then we design the heat pump, size the loop field, determine how much heat is actually needed to be drawn from the ground. And then from that, we can estimate the upfront costs to actually perform the installation, and then the annual operating cost to actually provide heat to the building, which is done with electricity rather than natural gas. So on the bottom of the screen, I have the dimensions of my house. It's about square in footprint, 40 feet by 40 feet. I added the quarter foot more or less to make the floor plan area accurate. And then the distance from the ground to the base of the roof is about 30 feet. So that'll be used to model it as a rectangular enclosure. But first, let's take a look at the actual heating bill. So the table in the middle right here represents the number of therms of natural gas that my house uses on a monthly basis. And you can see most of the energy is actually used in the winter, with a peak actually in January, but this is shown as February because that's the actual bill date. Now, I estimate that I use about 935 therms per winter or per heating season. Some of that actually trickles into the summer, just providing heat to the water heater in the house, but the vast majority is used to heat the house in the winter. And here you can see I took the 940 minus 5 to give it 935 therms per year. Now, we need to understand what the heat demand is for a building, and to do so, we need to make use of what are referred to as heating degree days. And essentially, these are days that the temperature outside is below the set temperature of a building. Usually, the temperature of 65 Fahrenheit is used as the base for a heating degree day. And essentially, the number of heating degree days is the number of degrees below baseline heat for which the house actually has to be heated. So here we can take the 65 Fahrenheit that the house would be heated to minus the average temperature of the day and get 44. And so it would indicate, at least for day 1 of January, there would be 44 heating degree days accumulated. The next day is also 21 degrees average temperature. January 3rd is 22 degrees average temperature. The 4th is 25 degrees average temperature. So you can see heating degree days get calculated based on the average temperature for each day of the year. And then the cumulative number of heating degree days is essentially the summation of all of those. So 44 plus 44 is 88, plus 43 is 131, plus 40 is 171. Now, for the Madison, Wisconsin area, which is similar latitude to Platteville and similar climate in general, typical heating degree days over the winter heating season from roughly September 1st through, let's say, June 1st or so, the cumulative heating degree days add up to about 7,000 per year. Now, the heating degree principle was actually developed by the coal industry to determine when it is that they would have to make coal deliveries to provide residential heating back in the probably 40s and 50s. So, as I said, the first step is to model the enclosure, the building, as a rectangular enclosure. And so I took the dimensions of my house, just overly simplified dimensions, and modeled it as a rectangular prism. And then I can add so-called simulated insulation on the walls, insulation on the roof. And you'll notice this rectangular prism disregards the triangular shape of the roof because, at least in my case, no one lives up there. And so the heating up to 65 or 67 isn't really necessary in that case. Now we can determine the thermal power, that is to say the heat flow rate through the roof and wall of these enclosures if we have the area of the enclosure and the average or the R value of the wall and the roof respectively. Then we would use the temperature of 65, 67 Fahrenheit as the high temperature and then the variable low temperature T sub C that occurs outside. So this then is the thermal power, that is to say the heating rate needed to keep the building at 65 Fahrenheit. And at least if I use a composite R value, then I can use the total roof area and wall area, that is to say the sum of the two represented here, to calculate the heating load of the building. Now, there's a similar set of guidelines offered by the Federal Housing Authority that suggests you allocate 1 British thermal unit per cubic foot per heating degree day, at least based on the heating degree day base of 65 Fahrenheit. We'll see in a little bit that that actually over predicts typical heating needs. So we'll go with the equation that's in the yellow box up above. Now, to perform the information needed, we can actually draw information from weather data. In this case, it's weather data for Madison, the Solmet Station 14837. It's a little bit outdated. You can see the annual cumulative heating degree days for this year was actually 7,700 rather than the 7,100, which has been the case in more recent years. But nonetheless, it has all the data needed to take both approaches. As I said, we'll take the approach that uses the data in the yellow boxes, so average monthly temperatures, and then the total roof wall area exposed to the outdoors for the house in question. Now, a third form of power can be used and drawn directly from the heating bills. Now, that can be obtained basically from your natural gas provider, at least assuming you live in town, or if you can figure out your propane use over the course of a year, you can also use that to estimate the chemical energy going into the building. A fourth box is listed here just to illustrate that we can also consider supplemental solar thermal heating for these buildings if we know the total global radiation on a monthly basis and the area, in this case, it would necessitate roof area that thermal radiation can pass through. And then this Greek letter eta, looks like an English letter N, represents the efficiency of a collector that could be used to collect solar thermal energy. That's the latter portion of this assignment. It won't be addressed entirely right here, but at least it shows that the weather data provided, I think it was National Renewable Energy Laboratory collects this data for major cities all across the United States. But you can see it contains three of the four sets of information we need to determine the heating load, either using just the simple one-dimensional heat transfer through a flat plate, or the heat requirements for a cubic or I guess volumetric enclosure, or the solar radiation that could actually provide that thermal energy if we had a solar collector set up. So focusing now on the chemical energy, as I mentioned earlier, my house uses about 935 therms per winter, and I drew that data directly from the gas meter that's used to measure and bill me for the monthly heating that's used at my house. And we can even use the methane energy content of 55.5 megajoules per kilogram to figure out the actual thermal power or the mass flow rate of methane needed to provide that thermal energy. Well, let's focus on a comparison then of the three methods of determining heating load. On the one hand, I don't know exactly the R value of the house, but what I can do is use the measured chemical energy provided by the Alliant Energy, who provides my natural gas and electricity, and I can use that to determine the composite R value of the house based on the total exposed wall and roof areas. And I can also compare that at least to the Federal Housing Authority guidelines and see how accurate those are. So the plot on the right shows a comparison of the three approaches. The tall orange bars represent the Federal Housing Authority guidelines, 1 British thermal unit per cubic foot per heating degree day. And this, as you can see, greatly over predicts the heating requirements of the house. Now, the chemical energy, the blue box, is the actual natural gas that was used by the house, the 950 therms total over the course of the winter. So I plotted those, and then what I did was essentially go through and compare the monthly, basically the average temperature, the T sub C on a monthly basis, to the T sub H, which I set at 65 Fahrenheit, the total area of the roof and wall, the 6,425 square feet, and I just adjusted the R value until the gray bars, which represent the thermal energy calculations in the yellow backs up here, more or less matched the blue bars. And from this, I was able to conclude that the composite R value of my house is about 12. This can be done with virtually any house as long as you've got the heating bills and the exterior dimensions of the house. Now, as a supplemental aspect of this, I'll be looking at solar thermal augmentation of the ground source heat to try to raise the temperature and make it easier for the heat pump to actually heat the house for a given power input to the building. But that's not going to be included in this presentation. I just want to illustrate that there are four powers. These E dots represent power, that is to say energy flow rate, and four of them can be considered in these residential, commercial, industrial heating calculations. So now to introduce the actual team project assignment, heat pump for the mining museum. This is a photograph of sorts of the mining museum. You can see it's comprised of three buildings. The large rectangular building, kind of in the middle of the screen. A little to the left is a building that I call the connector, and then on the left-hand side is what's referred to as the gallery. Now, this was actually the original Platteville High School. The large building in the middle was the original school itself. Evidently, at some time, a gymnasium was built, and then the connector was built at the same time. It's since been adapted to a museum, but what I want to illustrate is just the green boxes here represent the rectangular enclosure that we're going to be considering in our simplified representation. And then all of these red rectangles on the bottom represent what are referred to as the ground loops used to provide the heat pump. So let's start off with just modeling the building as a rectangular prism, or three prisms in this case. First, I had to estimate the heights of each building. I had fair knowledge that the height of the main building, the museum itself, is 38 3/4 feet tall from the ground level to the roof line. Then I had to estimate the height of the connector building, so to speak. I estimated that was about a quarter of the height of the museum itself. And then the gallery or the former gymnasium was about 40% of the height of those buildings. So these are the actual blueprints. You can see the high school of Platteville, built in, I don't know, 18, maybe 1904 or something. And really what we're modeling is the rectangular enclosure going up to the roof line, down to ground level, and then width of the building. We're disregarding windows and doors, and the roof we're just kind of treating as a composite rectangle. This is a simplified approach. We can certainly take a much more detailed approach, but we wouldn't gain a lot and it would be too time consuming for a class project. Now let's look at the floor plan. Here we've got the rectangular shape of the museum itself. You can see 60 feet 3 inches or 60.25 feet. The total width of all three buildings is 137 feet 3 inches or 137.25. And likewise, this east display gallery is 62 feet. So I use those, basically the plan view and the elevation view shown here with the three rectangular enclosures that we're going to be modeling to use to estimate the heating load for the building. So the height of the gallery, 15.5 feet, the height of the connector, 9.7 feet, and the height of the building itself, 38.75 feet. Likewise, their widths, 83.25, 17.33, and then 40 feet, and then their depths of 62, 60.25, and then 58 for the connector. What I want to point out right here as well, the next slide, you'll see a table of data showing the area of the external walls. So the roof in this case of the gallery is 40 by 62. In the case of the museum, it's 83.25 by 60.25. And then I refer to the exterior walls as the left wall of the gallery, the right wall of the gallery, the left wall of the connector, the right wall of the connector, and then the right wall of the museum, as well as the front of the museum, front of the connector, front of the gallery, and back of the museum, back of the connector, back of the gallery. So what I want to point out here is that the connector, at least its left and right walls, are basically connected to the gallery and museum. So those are subtracted away from the total external surface area of the building, which are the areas that lose heat. There's no heat loss from the connector to the gallery or the gallery to the connector, nor from the museum to the connector or the connector to the museum. So this then is a tabulation of the areas of all surfaces that are exposed to the environment: museum roof, left and front and back walls, left and right walls, the connector, front and back, left and right, and then the gallery, roof, front, back, left and right. Now conveniently, the left and right walls of the connector add up to 1,200 square feet, and the left wall shares 600 square feet with the museum. I guess the right wall shares 600 square feet with the museum, and likewise the left wall shares 600 square feet with the gallery. So those are actually subtracted away from the total areas of the walls, and they give us essentially the exposed areas of the building, which add up to 21,991 square feet. I'm just going to round that up to 22,000 square feet in the forthcoming calculations. So now we want to cross-check with the energy bills. It happens, this is the December heating bill for the Mining Museum. It was submitted on January 3rd of 2022. You can see that 1 month of December uses 934 therms of natural gas, costing around $773. Now, this is coincidentally nearly identical to the heating load of my house for the entire winter, which was 935 therms. So it really illustrates that the size of the building, of course, influences the heating requirements and also the imperative to try to improve the heating of the building itself. So let's start with just kind of an estimate of the thermal energy actually required by the building. I'll point out that a therm is 100,000 British thermal units, and one British thermal unit is the thermal energy contained within one wooden match. Now, we don't know the efficiency of the heater, but an estimate of 90% is reasonably accurate. And we can use this to figure out the actual hourly heating load for the building, average hourly heating load for the building in the month of December. If we take our 934 therms, or 93.4 million British thermal units for the month of December, divide by the number of days in December and the number of hours per day, we can reach around 113,000 British thermal units per hour. Now, from that and from the external area of the building, we can now determine the composite R value of the building. So we can return to our thermal power equation, thermal energy flow rate equation shown earlier. In this case, we can plug in the actual values. We want the building heated to 67 Fahrenheit. On the average temperature for the month of December is about 21.9 Fahrenheit. So this is our T sub C. We know the area of the building is 22,000 square feet, the exposed area. And then we saw the average hourly heating load for the building is 113,000 British thermal units per hour. So this, you can see, is actually the solution of the thermal power equation from up above, where all I did was equate the chemical power to the thermal power and then solve in terms of the thermal power for the R value. And so this shows me that the R value for the museum is about 8.8 hour feet squared Fahrenheit per BTU. My house was about 12, so shows it was better insulated and not subject to as many significant losses. Now we want to calculate the maximum heating load. And to do this, we can return to the thermal power equation we saw earlier using the area of the exposed walls and roof of the building, the composite R value that we just figured out, the indoor temperature that we want to maintain, and then really the coldest outdoor temperature that we typically see in Wisconsin, so negative 40 Fahrenheit. This would imply that we'd need around 267,500 British thermal units per hour to keep the museum at 67 Fahrenheit on the cold days of winter. Now, I was able to actually cross-check this result. A colleague of mine, John Hilliard from Train Technologies, used Trace 3D software to quickly model up the building, in this case also using rectangular enclosures. He put some windows in as well, and he determined for a similar temperature that the building would require 295,000 British thermal units per hour. And so that's in range with the calculations performed here. And we can estimate maybe 270, 280,000 would allow us to keep the building warm. On the coldest days of winter, negative 40 Fahrenheit, there's often a recognition that you can concede a little temperature, maybe into 60 Fahrenheit for a few hours, knowing that negative 40 doesn't usually last for more than a few days. So now we want to look into the ground source heat pump that we have to make use of. These use the stable temperature of the earth, and they use that to evaporate a refrigerant, which may be liquid or may undergo the vapor change around 30, 40 Fahrenheit or so. So it turns out ground temperature does vary as a function of the time of year. So here we've got ground surface temperature showing a pretty distinct sinusoidal wave, more or less lagging slightly behind the outdoor temperature. And then as we go deeper and deeper down from 2 to 5 to 12 feet, you can see the ground temperature actually really stabilizes. For this figure right here, we can see the average ground temperature is around 62 Fahrenheit, and we can conclude that this is a more southerly region of the United States. Here's an actual ground temperature map of the United States showing more or less the mean ground temperature at depth. We in Platteville in Wisconsin are right around this isotherm right here, somewhere between 42 Fahrenheit and 47 Fahrenheit. So I asked the students to use 45 Fahrenheit as the ground temperature for their ground source heat pump source temperature. Now we actually have to look into designing the heat pump. I'm just kind of giving the operating extremes for this. The students themselves are required to do this as part of their Chapter 10 homework project deliverables. But really what this illustrates is we want to use a refrigeration loop, essentially acting in reverse, at least for the heating mode, to pull heat from the earth, which is essentially an infinite reservoir at 45 Fahrenheit, send it through a refrigeration cycle that actually dumps the heat into the building in excess of 67 Fahrenheit. Typically, like 85, 90 Fahrenheit would be the actual temperature that the ductwork would use. Now, looking at the ductwork itself, these are blueprints for the HVAC system for the building. This enclosure on the bottom right here actually represents the museum, the connector, and then the gallery that we saw several slides back. And in the basement, kind of in the heart of the museum itself, is the big natural gas heater. And these are all the ducts going through various rooms throughout the building. Now, what a ground source heat pump would do is essentially replace the natural gas heater with the condenser, the high temperature heat exchanger of our refrigeration loop, and send the refrigerant through the cycle, kind of shown in this figure right here, where it would dump thermal energy, Q dot out of the process, pass through a throttling valve, undergo evaporation in the ground source wells, before it's recompressed and sent to the condenser again. So the benefit, we could say, of a heat pump is that the heat source essentially comes from electricity, from an electrical compressor, and it has the ability to multiply the energy going in by 3 or 4 times to provide pretty economic improvements, economic sources of heat, and an improvement on maybe conventional natural gas heating systems. So to return to the figures we saw earlier, this represents a simplified schematic of a ground source heat pump showing the evaporator, which is essentially the geothermal wells, the compressor with an efficiency of around 90%, the condenser with an effectiveness of around 90%, and then the evaporator with an effectiveness around 90%. So for the students who will be doing this project, these are the values you will need to use to figure out the thermal energy into the system and the power of the compressor required. So earlier we saw that the heating load for the building was around 267,000 BTUs per hour. And then the comparison done with Train Trace 3D brought it to around 290,000 BTUs per hour. So if we oversize it a little bit and round up to 300,000 BTUs per hour, we can assume with fair confidence that we would be able to heat the building. Now, what the students are assigned to do is figure out if the condenser is 90% effective, how much thermal energy has to come out of the refrigerant to provide 300,000 BTUs per hour. And if the evaporator is 90% effective, how much thermal energy has to come out of the ground to provide 300,000 BTUs per hour. And likewise, if the pump is 90% efficient, how much compressor, 90% efficient, how much compressor power is needed to run the system. So we'll be looking into pressure enthalpy diagrams to actually determine the operating points of the system. These can work for both air conditioning and heat pump systems. And just to give you a sense of how it can be applied, we need to set the condenser saturation temperature, topics from Moran Shapiro, Chapter 10. We also need to understand the condenser outlet temperature, including the subcooling that may be necessary. And for air conditioning mode, at least, we want to understand the summer ambient temperature, which the heat exchangers may be more or less fighting against to keep a building cool. Likewise, we need the compressor inlet temperature, evaporator outlet temperature, and evaporator saturation temperature in order to appropriately size our equipment to perform both as a heat pump and as a air conditioner. So it's not only sizing the equipment, but also setting the so-called operating points, that is to say the saturation, pressure, and temperature of the system, as well as the superheat and subcooled required to get the performance we want. Now, this then represents our refrigeration cycle in pressure enthalpy terms, and we can get an estimate of our operating points for the condenser and the evaporator shown here. And we can also get a sense if we enumerate the points on the refrigeration cycle. One is the entrance to the compressor, two is the entrance to the condenser, three is the entrance to the throttling valve, and then four is the entrance to the evaporator. We can use these points to figure out the coefficient of performance of our system by determining the enthalpies, small letter h's, at all of these points. And likewise, we can use that to determine the thermal power going out of the system, thermal power going into the system, and then work or compressor power required to make the system operate. And this then can be used in our coefficient of performance equation, beta right here, which allows us to determine the best operating points for our system based on the heat load required, the environment we want to heat to, and then the ground temperature of the system itself. Now, the last part is to size the heating field, size the loop field, I should say. And to do this, we need Q dot into the system, which, as you saw, can be extracted from the effectiveness of the heat exchangers and the operating points of the refrigerant that we select. So to give you a quick overview, essentially a heat pump has two main options for sourcing the heat. One is a air source heat pump, as shown on the left, which draws the heat from the air, and the other is a ground source heat pump, which draws the heat from the ground. Now, the drawback of air source heat pumps is in the dead of winter, when it's 0 Fahrenheit or even -40 Fahrenheit, there's no real heat to provide. And so they kind of bottom out at a certain low outside ambient temperature, maybe 0 to 10 Fahrenheit. And even in those areas, they just don't provide a lot of heat. Meanwhile, our ground source heat pump in Wisconsin, in this region, is 45 Fahrenheit. And so it does have heat that it can provide even when it's -40 Fahrenheit outside. So the remainder here are just some guidelines as to how it is to size a heat pump. In this case, the rule of thumb, so to speak, is 150 feet of depth will provide 1 ton of refrigeration, that is to say 1,200 British thermal units per hour, and it requires 3/4 inch pipe. Meanwhile, 450 feet of depth will provide 3 tons of refrigeration, or 3,600 British thermal units per hour, and requires an 1.25 inch pipe. Now, estimates for the cost of well drillers to actually drill each well is about $3,500 to $4,000 per ton of refrigeration, which corresponds to heat ability as well. And likewise, in order to avoid depleting the ground source heat, the spacing for cooling and heating wells is of the order of 10 to 20 feet. 20 feet is fairly optimum. You don't want to cool the ground temperature, diminish your supply of heat. And then the actual working fluids of these, we nominally say water, but it's actually more like water antifreeze mixture. And you can actually even use methanol in these processes. Now, the remainder of this for students to deliver as well is to provide an estimate of the upfront costs, that is to get the compressor, heat exchanger, throttling valve, piping network, as well as drill the wells, and then to use the required annual compressor power and the corresponding energy required in that to determine the actual operating cost and determine if substantial savings are realized by switching from natural gas supplied heater to a ground source heat pump, which uses a compressor with electricity to operate.